It's a singleton list that only contains the current state. And the interpretation of get is the same as before because get does nothing interesting with respect to the memory location. But the case with put is different from the previous slide, right? The put says if you want to put B into the memory location and run M, I'm going to make a function for it, and I'm going to assume I have Latin expressions in the semantics domain. So I'm going to first interpret M by passing the current state, the current Boolean value that I just put, and I know that I'm going to get back a tuple. And the tuple I get back will store the current value I want, as well as the states that we will see in the rest of the computation if there are more puts. And we are going to return the tuple that includes both this M, and we are going to add B to this list. So now we have one more item in this list that keeps track of that you have done this operation put B before. Right? Yes?
I'm a little confused on the S in the lambda and also the X that is
That's a typo. I should have named this differently. This maybe should be SS, not the list of S. But there are two different S's.
Okay, so the lambda S is not actually used.
Right, it's ignored because we are putting a new value. Okay, now we have this second interpretation, right? And you can ask the same question. You have this set of axioms. Now, is this interpretation sound and complete with respect to that set of axioms? Yes?
No.
Why?
Because putting something twice adds to the list twice, so it's not easy.
Exactly. Great. So we can show that this interpretation is at least complete with respect to the equations. So if two programs are equivalent under this interpretation, then you can actually show they are equivalent under the axioms, but not the other way around. And to disprove that, if you want to show that it's unsound, you only need more example axioms, right? And in this case, exactly like what you said, the put axiom will break, right? If you try to put it twice, under this interpretation, the list you returned will have two values because you have put two things into the memory location. And on the right-hand side, you will only have one item in the list because you have only done put once. So this shows that, well, you can give different interpretations to the set of operations, right? But the interpretation you give, it may not be sound or complete with respect to a set of axioms. But in this case, it is at least complete, but it's not sound. And I have one more example interpretation, which is a dumb interpretation that says let's just ignore the state because I don't care about the state at all. So in this case, you can interpret x again as a function because you still take this memory, but you are not going to use it. And you just ignore it and you just return exactly what this x is it will return. And so under this interpretation of the constant will be a function that doesn't care about this s at all and just returns c. And put is again similar as before, and get is again similar as before. And in this case, put, I think I need to pass b to this m because it's still a function, even though it's not used. And this is, of course, a very dumb interpretation, but it's also possible, right? Sometimes, maybe under certain contexts, you don't care about the stateful operations at all, just want the computation to run. And now the question, is this interpretation sound and complete with respect to the set of axioms? Yes?
It's sound but incomplete.
It's sound but incomplete. Exactly. So it's sound with respect to the equations because it actually equates more programs, right? Because you don't care about this get and put operations at all, you don't care about the state at all. The computation will be wrong just as it is. But it's certainly incomplete because programs that are equivalent under this interpretation, right? They are not equivalent under the set of axioms because you can put something to it But because the state you don't care about the state, that this program is exactly the same as M under this interpretation. But of course, they are not equivalent under the set of axioms. Yes.
I'm a bit confused that, so the S on the get, is that just propagated in all the time?
Yeah.
Okay.
It's propagating all the time. I should have a B here as well. It's just ignored in the end.
How is it successfully ignored if it's used to branch on ifs?
Because ultimately, let's see. Well, I guess you still need to access the state in that get case. It's just ultimately you are not outputting that state. That's a very good point. Yes.
So with respect to soundness, can you get unsoundness from like definitions like this if the like effect comes back into play as like a value in the program or expression, and then like you could end up with like it matters. Like if you discard it like this, and then it comes back like if you put B, but then later get it back into the expression again, like with the get, could that like I don't know. Can soundness still hold like in situations like that?
I'm not sure I get the question.
So say, so it looks like in this example, right, we're discarding the like
The final
effect.
state result. Yes.
Yeah, discarding it altogether.
Mm-hmm.
But like discarding that could like affect the evaluation further down the road, like if we do a get from the location. So does soundness still hold under a situation like that?
So I think you still pass around the state. It's just ignored and in the constant case. So like in this case, you will still do this if then else on the state, and then in the put, I'm missing a B, but you still need to pass the B to this computation. It's just ultimately, once you get the value out in the end, you will say, let's ignore this S.
Okay, thanks.
To add to this question, like what if you just say put true and then you get it? Then, isn't that unsound?
If you say,
on, then the equation isn't satisfied. It says like if you do put and then get, you get the branch corresponding to Boolean.
so you ask.
Is a no up.
But put true doesn't pass true into the state. It uses the previous state that was passed in. Like the way I see it is this is just a reader mode.
Okay.
Yeah. So you pass in the initial state, your reader state, and it just passes it along all the other computations without modification.
But one of the equations said like if I had to put true and then get, and then some branch and some other branch, that would be the first branch. It would be equal to the first branch, right?
No, because if the original state was false, that put true will not put the true in.
Oh, there's a typo on the slide. The definition, of course.
It should be MS, right? Not
Should be
MB.
I think it should be MB.
MB.
Okay, yeah. Okay, then it makes sense. So there should be no lambda. It should just be MB, like the notation of MB.
There is still lambda because you have to make a function.
Okay, so take S and then MB.
Right. Okay, so that's all about one specific example we have seen with get and put and with different interpretations for it. But let's see more examples of algebraic effects, right? We said that an algebraic effect is given by a set of operations and by a set of axioms that we would expect the operations to respect. So as a second example of algebraic effects, we can consider exceptions. And we can consider there is a class of exceptions that your program can raise. So I will use this subscript B. So it's like put T, put F. Maybe there's some raise divided by 0, raise like file not found, or something like that. And the arity of raise is 0, because you have performed an exception. So there is nothing, no computation that will run after you have raised the exception. So raise does not take any single computation. And because of that, of course, the axiom for race would also be empty because there's nothing really you can say about race. And on the slide, I also gave one interpretation of exceptions. So you can interpret exceptions as a sum type, right? It's either that the computation runs and give you back something in X, or you raise the exception and then you get something in this capital E. And the interpretation would just be like, if it's a constant, then I'm going to wrap it on the left, and if it's an exception, I'm going to wrap it on the right. So you can also consider this as the either monad, for example, in Haskell. And another example, one more example that we will discuss is non-determinism. So let's consider we have an operation OR, whose arity is 2. So again, it takes 2 commutations. And you can read this OR and M as something that non-deterministically runs M or M. Right? You don't know which one is going to be run. It's going to be non-deterministic. And there is a set of axioms that we can expect this operation to respect. So for example, if you non-deterministically run M, and then non-deterministically run N and P, then it will be equivalent to if you change the associativity, so you would not deterministically run this computation that itself non-deterministically runs M and N, and non-deterministically run it with P. And of course, if you non-deterministically run computation M or M, it's going to be equivalent as if you non-deterministically run the computation N and N. And if the 2 computations are the same, then there is no non-determinism. You know that you are going to run M. And the interpretation on this slide, it is we are interpreting X into a collection of non-empty finite subsets of X. So you can consider this as basically collecting all the possible execution passes of your program. So if it's a constant, then it's just going to be a singleton set that contains one C element. And if it's an operation M and N, it's going to interpret M and interpret N and create a union as the set operation. So you collect all the possible values that this computation could produce. And you can verify that I believe this interpretation is sound and complete with respect to the axioms. Well, I'm not showing that as an example on this slide, but another interpretation, right, for example, you can give to this OR operation is you associate a probability. Right? Maybe we run M with 50% possibility, and maybe we run M with 50% possibility. That could be another possible interpretation, but is the interpretation sound and complete? Mm-hmm.
You would have creativity and absorption, but not associativity?
Yes. Well, if it's 50%, yes, you have creativity, but you definitely don't have associativity. Yes. So you can see, again, this is like, you can always come up with different interpretations of the operations, but then you don't necessarily respect the axioms. So just to summarize a little bit and make a few remarks. So we have, yes?
Are there ever cases where there are multiple different interpretations that do respect the axioms and like under one you choose depending on the intensity of the program?
That's a very good question. I believe so, but I cannot give you an example right now. So as we said, an algebraic effect is given by a set of operations, and you can consider them as effect constructors, right? Because if your program wants to raise effects, they have to have something to raise effect with. And these operations, they come with signatures, and we have seen examples like get and put, and exceptions, and the non-determinism example. And they also come with a set of axioms. And perhaps this is related to some of the questions you asked me before, because when you say, okay, there's a set of axioms, how do I know if this set of axioms is the right set of axioms? There are just some properties you can say about the set of axioms. So if you have a set of axioms, then you can actually write a whole deductive system with it, and you come up with a whole equational theory. And we will say this equational theory is equationally inconsistent if you can use it to prove equivalence between two distinct things. Like if you just say, well, I will use it to prove x is equivalent to y, and that is bad, because you can basically prove equivalence of anything. And then that's saying about when the equation of theory is bad. But how do I know if the equation of theory is good enough? So we say equation of theory is Hilbert post-complete if you adding any unprovable equation will make it equationally inconsistent. So a few things here, right? Here we are adding an unprovable equation. So this also relates to the previous question, like under this set of axioms, there are lots of things that you can actually derive, or you can actually prove. And of course, adding these kind of things will not hurt, but it also will not increase the expressiveness of the set of axioms, because you will be able to prove exactly the same set of equations that you would have been able to prove before. And if you add any kind of unprovable equation to this set of axioms, if it makes it equationally inconsistent, the equation of theory inconsistent, then we know that the set of axioms you have now is already good enough, at least in the sense of Hilbert's post-complete. Yes?
And this means if any unprovable equation that we could add would make it equationally inconsistent, right?
Mhm.
It's not right.
So you can prove, I think for example the non-determinism one is Hilbert complete, Hilbert post-complete, and that can be done usually by a contradiction. Like if you add an equation that relates something, and in the end you will be able to derive x equal to y. Yes?
Maybe a little bit of a notation question, but when we're talking about equationally consistent things, x and y, what do we, like, in this case, what does x equal y? What's the equal and x equal y mean?
Right. So if we have set of axioms, right, you can write equations with it, right? Like for example, we have seen get will give you like the same get, but you can actually instantiate that m and n like as different things, or maybe you can just consider them as like abstract variables that could represent different kind of computations. But you expect this axiom to hold for any m and n. So you can actually have a deductive system, right? By applying these axioms, you can derive equations between programs. Because you can apply rules in sequence. If you first reduce get and get, you first then reduce get and put. And this becomes a whole equation of theory. Right? You have the axioms and you have programs that you can relate. And in the end, if you can actually prove x is equivalent to y for like a different x, and like x is different from y, that if this is provable under that equation of theory that consists of that set of axioms, then that is considered equationally inconsistent, if that makes sense. Like you go from the axioms to things you can derive, and that becomes the equation of theory, and now these things, like if you can actually apply that equation of theory to prove x is equivalent to y. Yes?
So you said x different to y, different in what sense?
So you can consider you started with different things, right? You will say, let's say there is an x and there is a y that is different from x. Then maybe there are computations, maybe there are constants. Like for example, in the end, you are able to prove that true is equivalent to false. It's just in this case, it's not necessary to talk about the specific value of the variables. You can consider them as abstract things that can stand for different computations or values. But in the end, you will be able to prove that they are equivalent.
So is this understanding correct that I first come up with some interpretation or behaviors that I want this program to be, and then I consider different means different behavior or different in such interpretation?
You can consider them as different. Okay.
Otherwise, I think that if you have different, basically comes from your equational theory. For example, if you have if your equation theory consists nothing, then x equals y only if and only if x is exactly syntactically the same as y.
Mm-hmm.
But if your equational theory defines that get equals to something, then these two becomes equal. But other than that, they are different, right? So this different is syntactically different, or it's modular the equational theory. So I think it seems like to me that this definition of equational inconsistent is kind of cyclic.
I'm not sure I understand that, but I guess it depends a lot on what you have in that theory. Like in this case, right, for example, we consider, in the case of get and set, we could consider we have the set of operations and then we have true and false.
Yeah, so I mean,
right, and then you can actually write programs with true and false and with operations, right?
Yeah, so I mean, different can be in two senses, like one is in the syntactic sense, which relates to the equational theory. That is, if you can prove that x equals y under your equational theory, then they are not different. And the other sense is in the semantic sense, which you'll come up with some interpretation first, and then you consider x and y to be different if they are different. If they are different in your interpretations, basically. And I guess this equational inconsistent means that if x and y are different semantically, then you cannot prove x equals y.
I would think so, because it's not, at this point there's nothing about the syntax to some degree. The axioms are talking about, well, there is this set of operations, but then it's abstract over other things, right? And we will just say, let's consider there's some x and some y, and they are different. But in the end, your equation will be able to prove equivalence between arbitrary things. Basically, this is what it says. Because x can stand for anything and y can stand for anything.
Or, so you mean that this property basically says that I can prove arbitrary x, or yes, a universal quantifier over x and y.
Right, because you don't care about what x and y
okay.
are, and then you can prove their equivalence. Okay. Yes?
Sorry, so to summarize, if I'm understanding right, the x equals y, this means you start with x, you use the equational theories, axioms to move around, and eventually you end with a y that you didn't start with. And it's just about like manipulating the symbols, right?
Yeah.
It's nothing.
Yeah.
Yes, so this looks a lot like many sorted universal algebra, but like, so if we have an equation, right, that could in general, it's in an arbitrary type system, that could have a whole bunch of things. Like, in order to talk about equational completeness or incompleteness, like, kind of what do we do if there's like an axiom or a polymorphic, we just instantiate it with every concrete type and then say like, look at that, or what? My question might not be.
I'm not exactly sure about that, but we can talk afterwards. All right. Okay. So we have also seen different interpretations of the same set of operations, right? And then we talked about this set of axioms. But in practice, of course, different interpretations, they are sometimes useful as well. Like for state, maybe you do want to keep track of everything that has happened for debugging purposes, for logging purposes. So sometimes people do use effects without equations. But it's generally useful to keep the equations in mind when you program with effects, as that will help you reason about program practice. And this is especially, this like programming without equations is especially true when we introduce effect handlers, because people can write different interpretations of effect for operations at different handlers and without caring about equational theory at all. So far, we have, what have we talked about? We talked about an algebraic effect is given by a set of operations with signatures, and they have a set of axioms. But the one question I often got asked from people when I talk about algebraic effects is, well, what is algebraic about algebraic effects? Right? There must be some definition of algebraicity. Okay, this is what I take from the literature. So this gives you, at least to tell you, there is a very, very precise definition of being algebraic. And of course, you probably cannot make a perfect sense of this definition now, but from what we have just discussed, maybe some of the terminologies will already start to make some sense to you, or at least related to what we talked about before. For example, we start with the equational axiomatic theory. So this is a set of axioms we have seen. And then for any set of variables, x, so it's abstract over the set of variables, so it's like m, n, x and y. And also operation symbol op with signature n. So we have seen before that exception has arity 0, or has arity 2. And we have the following function because operation is something that takes n tuple of this kind of computations and returns you a computation. And then if there's any other function f that maps the set of variables in x to basically the free monad, free model, free algebra of the same set of axioms but over different sets of variables, then this diagram, and then this f dagger is a homomorphism. So in the sense that this diagram will commute. And we call such a polymorphic family of functions algebraic. So what's your feeling after reading this definition?
Trivial.
Okay, this is my first feeling when I read this definition in the beginning. But of course, if you are really get into category theory, and maybe you will start to make perfect sense of this definition, yes?
What is that dagger? Is that like the lift of F or something?
Right, so you can see this, okay, maybe I'm not supposed to extend this. But you can see the F has signature X to this thing, but here you want this F to go from TAXX to this thing. So you can consider this as a binder operation, for example.
So this, if I'm understanding correctly, TAX is like freely generated on X or something? And so
Right.
it's this
Yes.
mapping property?
Yes. So this is like the binder in that monad, TAX, basically.
Right.
Yes. So you see somebody starts to make sense of this definition already. But, well, the goal of my lecture, right, is not to talk with you about any of the algebraic, any of the categorical semantics of effect handlers, but rather how we can program with algebraic vector effect handlers. So here is the programming counterpart of being algebraic. Right, so we have this very precise definition of being algebraic on the previous slide, but how does it translate to programs that we will write? The definition will go like this. So first, we have the definition of evaluation context. I suppose some of you know it already, but it's basically just an expression with a hole, like this is a hole. But evaluation context also specifies the evaluation order of things. For example, in this case, this hole would first appear in this function argument. Okay, this is an application. It will first appear in this function position, and unless this function is already a lambda, then it will appear in this argument position. And if you have this definition of evaluation context, and you have an operation whose arity is n, then this equation should hold. And what does this equation say? This equation says if you perform an operation, because its arity is n, we know that it takes n computations from m1 to mn, and afterwards, after the operation is done, you are going to evaluate E, because E is the evaluation context that says that what comes afterwards. Then it's equivalent to if you push this evaluation context into all the computation arguments to this operation. Right? So it's basically saying if you perform operation with arguments from M1 to Mn, and then you do the evaluation context E, it's equivalent to if you do this operation directly with the evaluation context pushed in to the operation arguments. Yes?
So the contexts are like pure, they don't contain any effect being involved themselves.
That's a very good question. For this, yes, if you try to keep pushing this evaluation context, you have to stop when you see an operation. Because you don't know how the operations would commute or interact with each other. And we can apply this algebraicity property to the examples we have seen in the previous slide. So for example, if you raise an exception, and this exception, well, because raise has error is 0, there is no computation argument, and you apply it as a function to m, then you know that because this exception has been raised, this whole program is going to terminate, and it's equivalent to if we just raise this exception, and there's no m at all. And in this case, if you apply this equation, it will be trying to push this argument, the evaluation context, into the computation arguments, but you have no computation arguments, so no push has happened. And it's the same if this raise appears in an argument position. But this OR would be slightly more interesting. So you would say OR because arity is 2, so it takes 2 computations. And after this OR is done, you are going to apply whatever you get from OR to argument P. Now this is equivalent to if you just push this P into this argument, into the computation arguments. And now you are choosing between MP and NP. Right? So if we consider it intuitively, what is happening? We are going to non-deterministically pick a computation M and N, but once it's done, we know that we are going to apply the result to P. And this is equivalent to if we just non-deterministically pick the computation MP and NP. And similarly, if this OR appears in an argument position and you have a lambda that waits for it, then you can also just push the lambda inside the computations. And now you are not deterministically picking these 2 computations that both have lambdas applied to them. Yes?
So just to make sure I understand, in the top left, the evaluation context is whole, and on the top right, the evaluation context is like whole P, and so on. Like in the bottom right, it's going to be lambda XP whole. Okay.
Exactly. So I'm writing these expressions as I have plugged in this OR into this box. But if you actually want to write the evaluation context down, in this case, it's going to be lambda with a box. And then this whole evaluation context is applied to this OR in the sense that you just plug the expression into that hole of that evaluation context. Yes?
Can this system handle programming languages with user-defined exceptions? So it's effectively open-ended, unbounded. So it would not.
Can we handle user-defined effects?
User-defined exceptions.
User-defined exceptions. What does user-defined exceptions mean? Like you,
So there are several programming languages in which the exception system is extensible, and it's not a predefined, hard-coded list of exceptions.
Mm-hmm.
So what I'm saying is, in these examples, it looks like it's all predetermined what your list of exceptions can be in your model.
Mm-hmm.
So I was asking what about those programming languages where the exception system allows the programmer to add an arbitrary number of exceptions?
Right. You can definitely extend that with like more different kinds of exceptions.